following directly on from my previous video where we looked at linear programming and solving two-dimensional linear programs graphically, we're going to have a look at a minimization problem this time. So still two-dimensional case, still using vertex testing methods, and but this time it's going to be a minimization one. Okay, so here is my linear program. This time we can see it's a minimize rather than a maximize. And also typically we use the letter C for minimization problem, although it doesn't have to be the case, of course. C for cost. Okay, we tend to want to maximize P for profit and minimize C for cost. All right, but in reality, it could be anything. So here's my objective function, C equals 9x minus 2y, and that's what I'm going to try and minimize, subject to these constraints. Now in this question, I have 1, 2, 3, 4, 5 constraints, okay, which I need to have a look at. So in the previous video, we looked at kind of where these graphs crossed the axes so that we could draw them. In this question, it's going to be less easy to do that because there's lots of kind of negative points on the axes where they cross. So I'm actually just going to give you where the axes are going to need to be. So in this case, we're going to go up as far as 30 in my y direction. Okay, so there's my 30. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Doing that because that seemed to fit quite nicely on the screen. That's a 15. And then we're going to have a 0 there. And then we're also going to go 30 horizontally as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's put 30 there. Okay, so there's my x-axis. 30. 1, 2, 3, 4, 5, there's 10. 1, 2, 3, 4, 5, there's 20. Okay, so slightly different scales on my axes, but it is 30 to 30 in both directions. Just like in my previous video, I will color code each of these constraints so we can see them nice and clearly. So the first one is going to be orange. It is just the line y equals x, so it's going to have a gradient of 1. Just be careful because the scales aren't the same on both axes, so it's not quite going to be 1 according to the squares. But if I go from 0 to 30, 30, then both of those points will lie on that line, so I can join both of those up with a straight line. There we go. And this is another one of those constraints which has gone through the origin. So to decide which side of the line to shade, I need to choose a point. And we can see that y is bigger than or equal to x. So if I choose x is 0, I want the y-axis to be included, the positive y-axis. So I'm going to shade then the underside of the line so that all of the points above the line satisfy the inequality which I want, which in this case is y is greater than or equal to x. Okay. All right, the next one is this one here. So it's going to cross 15 on the y-axis because when x is 0, y is 15. So it goes there. Now when y is 0, x will be 30. So I can plot that one as well. So that's going to go down to there. So this is one that I can draw them both up on the axes. Okay. And again, good habit to label them. So this was x plus 2y is greater than or equal to 30. Useful to do so that you know which ones to solve simultaneously when you need to do that. And then to decide which side of the line to shade, plug the origin in, 0, 0. It's not greater than 30, so I don't want the origin. So I'm going to shade the underside of that constraint. Okay, that rejects then the origin from that constraint as the origin doesn't satisfy it. Okay, the next one is nice and easy because it is just a vertical line. Do this one in green. X equals 5. That's just going to be the vertical line at x equals 5. And now consider the constraint. X is greater than or equal to 5, so therefore I don't want the origin. So let's shade that side out. Okay. And that is x is greater than or equal to 5. All right, so that's 3 down, 2 to go. The next one, let's do it in red. We've got 4x minus y is greater than or equal to 4. So when x is 0, y is minus 4. So it's going to cross the y-axis down here somewhere. So it's not very helpful. But when y is 0, x is 1. So I know it's going to go through the 1 on the x-axis. Also, it's got a gradient of 4. So when I go across 1, I'm going to go up 4. Alternatively, if I go across 1, 2, 3, I'm going to go up 12. And I've chosen that because 12 is a scale on my axis because it goes up in 3s. Okay, so I can go across 3 again, 1, 2, 3, and then up 4 essentially, 1, 2, 3, 4. And then I could go across 1, 2, 3 again, and then up 1, 2, 3, 4. That's off the page now. So it would go through that point next. But I only need 2 points to join a straight line together. Something like that. There we go. All right. And again, through the origin in, origin is not satisfied because 0 is not greater than 4. So I do not want the origin. Yes, yeah, I don't want the origin. So I'm going to shade the side of the line with the origin. There we go. Right, so there's my origin. It's not satisfied, so I've shaded that side of the line. And then one final one. Let's do this in a kind of a darker green colour. Y minus 2x is less than or equal to 10. When x is 0, y is 10, which is going to be 369, about there-ish. And when x is 0, y is minus 5. So again, that's got a negative value there. So it's not very easy to draw that. Not in this graph anyway. So let's choose some other points. Let's try when x is 1, y would be 12. Okay, so 12 minus 2 is 10. So x is 1, y is 12. That's going to be there. Or if I choose x is 4, y will be 18. So that's going to be that point there. And I can choose more points as well if you want to, but like I said earlier, you need 2 points to define a straight line. Okay, that's my constraint line there. And finally decide, does the origin satisfy it? 0 is less than 10, so yes, the origin does satisfy it. So I want the side of the line with the origin, so I'm going to shade the top side of that. Okay, so that's given me this. Right, so those are my constraints graph. That's all 5 of them. Now what we notice in this case is we have one constraint going up that way, one constraint coming down here, another constraint there, that blue constraint then brings it in there, and then the orange constraint takes it up there. But there's no constraint kind of bounding the top end of this feasible region, which makes the feasible region actually an infinite region, infinite area. It spans off in that way. This has got a gradient of 1, and this green line has got a gradient of 2, so they're going to diverge away from each other. So you've got this infinite shape now, which just shoots off in that direction. And that's not uncommon in minimization problems, because we've got to minimize the objective. So we want the smallest value that this can be. But the principle remains. We look at all the vertices of this feasible region. We calculate them, and then we run them through the objective function. So in this case, there's 4. We've got A there, which is the intersection of the red and the green. We've got B there, which is the intersection of the red and the light green. C is the intersection of the light green and the light blue. And then D is the intersection of the light blue and the orange. One thing I didn't do was I didn't mark on the rest of these equations. So that's 4x minus y is greater than or equal to 4. Did the orange one, did the blue one, did the green one, and didn't do the dark green one. So that was y minus 2x is less than or equal to 10. Okay. I do recommend you do that so that when you come to look, okay, I want to solve this point here, then I'm looking for the intersection of this line and this line. So then it's those 2 equations that we are going to be solving simultaneously to get the coordinates of A. Okay. So it's quite useful to do that, particularly when you've got 5 constraints kicking around. As I said in my previous video, this is not a course for solving linear simultaneous equations, so I'll leave you to do that yourself. But the coordinates of A are 724. The coordinates of B are 516. The coordinates of C are 512.5. And the coordinates of D are 1010. Coordinates, not from the graph, we're getting the coordinates from the algebra by solving them simultaneously. Okay, don't get these values from the graph because you need to know the exact points, and the graph isn't 100% accurate because you've drawn it. Okay, so don't use the graph to get the points, solve the equations simultaneously to get the points. Okay, and now C is 9x minus 2y. So I'm going to, just like before, I'm going to run all of these points through that objective function to give me a value for C at each of these points. So 9 times the x value minus 2 times the y value. So 9 times 7 minus 2 times 24. That gives me a C value of 15 at the point A. All right, and I'll repeat that for the other 3 points. So 9 times 5 minus 2 times 16 is 13. And then 9 times 5 minus 2 times 12.5 is 20. And finally 9 times 10 minus 2 times 10 is 70. Okay, so those are the 4 values of C at my 4 vertices of my feasible region. Okay. Now, minimize C. We want to take the smallest of these, which is this one here. Okay, B is the smallest because it's got a C value of 13. So the solution to this linear program is the minimum value of C is equal to 13, and that occurs when x is 5 and y is 16. Okay, that's the solution to the linear program. This is the vertex testing. This is the graph of the constraints in the feasible region, and there was my linear programming problem to begin with. Right. You can see how it's very similar to the maximization problem, except we're just taking the smallest value, and it is possible to get an infinite feasible region. Okay, that can also happen in a maximization problem, but the infinite feasible region will tend to go down that way. But the negatives in the objective function can throw that as well, so don't hold too fast to that. Okay, just don't be thrown if you have an infinite feasible region. All right. If you have any questions on this problem or any other linear programming graphical problem, please just pop a message in the comments and I'll get back to you when I can. Thanks very much for watching.